All right, this is the final video where we're going to finally come up with the mathematical equation to apply to be able to figure out which wavelength of light would be selected depending on the thickness of that oil film and the refractive index. Let's say it's 1.4. Okay, using those two variables, the exact thickness of that oil film and the refractive index, we can actually figure out is it going to be blue, is it going to be red, and we're almost there. Okay, so let's just review really quick. Okay, ray number 1, remember, is my reflected ray. And ray number 2 is my refracted ray. Okay, and what we talked about is when we looked at the reflected ray being reflected, we had to think about something called phase shift. Okay, I'm going to change to a better color than that. Okay, so ray number one that is reflected, does it undergo a phase shift or not? Okay, so it's traveling from air, which has a refractive index of n is equal to 1.0. Okay, so it's going from a low density medium to a higher density medium. So when that ray reflects, according to the last video, we said when it goes from low density to high density, it undergoes a pi phase shift. So it does undergo a phase shift. So ray number 1 has shifted by pi, or a half wavelength. Okay, so it is shifted by a half wavelength. That's important. Okay, so whatever happens to this light that got refracted in here, the path length that it travels has to come out with a half wavelength. Something, it could be 1.5 wavelengths, 2.5 wavelengths, 3.5 wavelengths, 4.5 wavelengths, but that light that comes out has to be a half wavelength difference. At least we think so. And that's so that these two waves can overlap and be in phase. Okay, if this shifts by half a wavelength, this has to be able to match up. Okay, it's what we talked about. If this was a trough, this needs to also be a trough right at that interface so that they're going to overlap. Okay? All right, so we got the idea about phase shift. We know that ray number 1 has undergone a pi phase shift, and it's necessitating a half wavelength integer. On the other hand, when I look at the reflection from the bottom, the oil is more dense than water. Okay, so at that point, that reflection down here, that reflection at that interface states that there is no phase shift. Okay, which really proves to me that that wave is going to travel without a phase shift, meaning that the number of waves that occur in here have to be on the order of a half wavelength when it comes out so that it'll be able to overlap. Okay, if, for example, that wave shifted and so did this wave, then everything is fixed. This shifted, that shifted, so they're going to come out overlapping if this is a full number of wavelengths. That's an important thing to look at, and in some example problems that I'll have in the next video, we'll be able to practice that a little bit more so you can understand it. So the first thing we look at is phase shift, and we try to analyze each reflection. There's a reflection here for a phase shift, and there's a reflection here for a phase shift, and that'll tell me to say whether I need to come out with half wavelengths or I need to come out with full wavelengths in order for things to be constructively interfered. Next, we need to think about the thickness of the film in here and how that thickness of the film is going to help us figure out the number of wavelengths that light travels inside of that film. Okay, so if I was thinking that that light is coming in at a very steep angle, and because this oil is very, very thin, you can imagine that that ray is almost perpendicular. It's almost vertical. Okay, so that light is going to travel 2 times the thickness of this film, 1, 2. And that distance will select how many number of wavelengths can come out. Okay, so depending on the thickness of the film and the refractive index, only a specific wavelength is going to match the requirements to come out. This reflected ray says that that light has to come out on the order of a half wavelength. All right, so whatever goes through here has to be 5.5 wavelengths, 6.5 wavelengths, 7.5 wavelengths. It has to come out as a half wavelength. And that's going to give me a very specific wavelength depending on this thickness. So the formulas that you have in your textbook, there's two of them for thin film interference, and I want to go over that. Okay, so one formula would look like this: 2 times the thickness of that film, okay, times the refractive index is equal to m lambda. Okay, so sometimes in your text it can either be t is equal to thickness, and sometimes d is equal to thickness. Okay, that can get a little confusing because there's a lot of little d's in many formulas. Another confusing thing is n. N in diffraction was order, but n here is my refractive index. Okay, so we're factoring in the refractive index because lambda divided by n, if I move that over to this side, is going to give me the new wavelength in this medium. So like I said in that last video. Okay, so this 2 times the thickness times the refractive index would tell me how many wavelengths have traveled in that medium, and is it going to be a full order of wavelengths? So m represents the number of wavelengths. Okay, and if m is an integer, 1, 2, 3, that's a full wavelength. Okay, and on the other hand, another formula is there right underneath it in your data booklet that has m plus 1/2. Okay, and I need to be able to select, do I use this formula or do I use that formula to be able to figure out which wavelength of light is going to be selected by that thickness of the film. And this m plus 1/2, or m, depends on the phase shift. Okay, and like we said over here, the phase shift is half a wavelength, and here I don't have any phase shift, so the conditions are telling me that I have to come out on a half wavelength difference. So this formula would be the one I would be using to describe this situation, because this is telling me that that wave has to come out on a half wavelength in order for it to be constructive interference. Okay, so if I knew the thickness of the film, let's say it's 100 nanometers thickness. Okay, so the film is 100 nanometers and the refractive index is 1.4. I'd be able to calculate the wavelength. And m, for the simplest case, for the very thinnest oil that I need, m can be 0. All right, so m can be equal to 0, 1, 2, 3 in this case. M can't be 0 here. M is going to be 1 in this case. But for this case, m is going to be 0 for the simplest case possible. So if I've selected this formula to describe that situation, okay, and I know that the film is 100 nanometers thick, I can plug all those variables in. 2 times 100 times 10 to the minus 9 meters times the refractive index of that oil, which is 1.4, is going to be equal to 0 plus 1/2, so 1/2 times my wavelength. All right, so then when I cross multiply, I would have 2 times 100 times 1.4 will give me whatever that wavelength of light is going to be. So it's going to be around 560 nanometer light, I think. Yeah, 400 nanometers, 4 times, yeah, it's going to be 560 nanometer light would be what's selected. So that would mean that 560, I think that's probably like a yellow greenish color. Okay, maybe orangish. Okay, so 560 nanometer light coming is going to be the only wavelength of light that would be able to go through that oil and match up constructively. So that would tell me what color that thickness of film is if it's 100 nanometers thick, okay, under that situation. So in the next video, I'm gonna give you 3 or 4 problems, and we're gonna practice applying this formula and this formula to be able to figure out what color that film would appear due to constructive interference.